Now let us consider the isentropic efficiency of pumps and compressors. A pump is specific to handling liquids and a compressor is specific to handling gases. Now when these devices operate and there's an increase in entropy, this results in an associated increase in enthalpy, which requires the device to have a greater work input to achieve the same result. The isentropic efficiency is defined as the ideal quantity per the actual quantity. That is, the isentropic efficiency of a compressor or pump is H2S minus H1 per H2 minus H1. We note that H2S minus H1 is the ideal work into the system. This is going to be the minimum amount of work to go from state 1 to state 2S. The actual work, H2 less H1, is going to be greater. Thus, our efficiency is bounded between 0 and unity. Note that this expression is opposite of turbines, nozzles, and diffusers. Now let's consider a situation where a steady-state air compressor takes air at 95 kPa and a temperature of 295 Kelvin and increases the pressure by a factor of 6. If the compressor has an efficiency of 82%, we want to determine the exit temperature of air. We start by noting that the work of the actual compressor per unit mass flow is given as H2 less H1. The work of an ideal compressor per unit mass flow is H2S minus H1. Therefore, recalling the definition of isentropic efficiency of a compressor, we have H2S minus H1 per H2 minus H1 is equal to 82%, or our enthalpy at state 2 is equal to H2S minus H1 per 0.82 plus H1. Now using EES, the enthalpy and entropy at state 1 are found to be 295.4 kJ per kg and 6.867 kJ per kgK, respectively. The enthalpy at state 2, considering an isentropic process, is found from the pressure, i.e. 570 kPa, and the entropy at state 1, that is, H2S is equal to 493.5 kJ per kg. Thus, the actual enthalpy at state 2 is 536.98 kJ per kg. The temperature at state 2 can be found based upon enthalpy, if we use our steam tables, or enthalpy and pressure if we use EES, and it is found to be 532.7 Kelvin. Now, in comparison to the ideal scenario where enthalpy at state 2, S, would be less than that at state 2, our temperature at state 2, considering an isentropic process, would be 490.65 Kelvin.